Okay, it's November 9th. I'm sitting here watching the Heat about to waste away a 20-point lead to the Utah Jazz. So I thought I would do an example for you from class today. We looked at vector spaces and how we can define a space and how we can check to see if it's a vector space given a defined subset, a defined addition, and a defined scalar multiplication. So in this particular example, our defined subset or set is going to be R2. That will be V. We have an addition, and the way we're going to add two vectors in R2 is U plus V is going to be equal to the sum of the first components, U1 plus V1, and the difference of the second components, U2 minus V2. Similarly, we need to look at a scalar multiplication. So for each scalar A, in this case, the scalars are all real numbers, A times U will always give you back the vector 1, 1. So we must check the 10 properties to see if they hold, and if the 10 properties hold, then we would say that this set forms a vector space. If we look at the first property, which is closure under addition, we see that clearly U plus V is in R2, and that just comes directly here from the definition. We see that the sum of U plus V as it's defined is a vector in R2. Similarly, we can clearly see that the scalar multiplication of A times U is also in R2 because that just comes from the definition. A times U is always going to be the vector 1, 1, which is a vector in R2. Now we can check the commutative property. So we want to check U plus V, which is equal to, from the definition above, the sum of the first two components, U1 plus V1, and the difference of the second two components, U2 minus V2. Notice that the first component in the subtraction of the second component there comes from the first vector. So it is U2 minus V2. If we look at over here, V plus U, we'll get the sum of the first two components, V1 plus U1. And then we get the difference of V2 minus U2 because that is the order that we're supposed to subtract them when adding them. And we notice that this vector is not the same as this vector because they differ in the second components. So we could stop here and we would know that this set with this defined addition and scalar multiplication does not form a vector space. But we'll check a few more of these properties just for the practice. So consider what happens if we add by the zero vector, and in this case the zero vector is the additive identity for this defined addition, because we see that if we take the vector U and add it to 0, 0, we get in the first component U1 plus 0, second component U2 minus 0, and then this gives us back the vector U1, U2, and by definition any vector that when we add it to a vector U it gives us back the vector U is by definition the additive identity. If we check a fifth property, namely we would be looking for the minus U for every U. We see that we have the vector U1, U2, and if we add that to minus U1, U2, we get U1 plus a negative U1, and in the second component we get U2 minus U2, which gives me back the zero vector, 0, 0. We know this is a zero vector given this addition from property 4, and we know that anytime we have a vector U and we add it to something that gives us the zero vector, then this vector that we added it to is what we call the additive inverse. This is the vector that when we add it to U, it gives us back the zero vector. Now from 5 we can see that for every U, the minus U, and this is just a notation for the additive inverse, will always be equal to the negative of the first component and the second component same. It should be also noted from this problem that minus U is not equal to minus 1 times U. Now if you go back up here and look at the definition of scalar multiplication for this problem, you'll see why. Now you should go ahead and check the rest of the properties. I'm going to go back and see what the Heat are going to do in overtime. Good luck.